Hello everyone. Today we will take an in-depth journey through the MapReduce architecture and Hadoop programming, the pillars that help us unlock scalable, reliable big data processing. Whether you are aimed to deploy system at web scale or just want to understand how what is behind Hadoop, this walkthrough will build a solid foundation. What is MapReduce? MapReduce is a programming model that revolutionized big data analytics when Google introduced it in 2004. Before MapReduce, processing massive dataset required complex code and expensive infrastructure. With the help of MapReduce, you can split a huge job into chunks, execute them in parallel, one on hundred or thousand of server, then combine the result automatically. Think of it like a recipe. Break the dishes into steps, let multiple chefs do the prep, and finally bring it all together in the end. MapReduce provides Hadoop's ability to process petabytes of data, making it the backbone for everything from search engine to specified analysis. Now let's go to the next topic, which is the master slave architecture. The master slave architecture, the heart of the robust map structure. There's just two things. There's a job tracker, the master or the coordinator. It receives jobs, split them into tasks, and assign this task into one working nodes for execution. It also tracks the status and progress. There is the task trackers, the slaves or the workers. Each machine runs once, responsible for executing map or reduce operation on the data local to that node. Why did this design? Distributed control means you show that there is never a bottleneck by one slow node. Fault tolerance is built in. If an task fails, job tracker reschedule the task on a healthy node, maximizing reliability and uptime. Third thing, it is a deep dive into fault tolerance. Failure detection. Job tracker pings task trackers at interval. If a worker doesn't respond, its tasks are scheduled elsewhere. Task reschedulation. Both map and reduce tasks can rerun seamlessly even during hardware failures without manual intervention. This is critical because on a large structure cluster, hardware or network hiccups are inevitable. Hadoop's approach ensures progress continues smoothly without any error. There are three main key features of MapReduce. First is the map phase. The map phase, the input data is divided into splits or chunks. Each mapper processes a chunk independently, converting raw input into intermediate key value pairs. Second is the shuffle and sort phase. Here, all the intermediate keys are intelligently mapped by groups and sorts. This redistributes data across the cluster so that every reducer gets all value of a specific key. Third one is the reducer phase. The reducer aggregates and summarizes this value per keys, producing the final results. Example: if you want to count the number of frequencies in a gigabyte of document, then what would you do? The mappers emit word one for each word. Shuffle phase group pair by word reduces sum count so you don't get the total occurrence per word. The next is the data locality. That means Hadoop is an innovative task maker. It provides data moving. Instead of moving huge dataset over all the network, Hadoop tries to process data where it is already stored in the HDFS. So why does it matter? 90% of traffic is reduced, increased throughput by 10x, enable truly scalable processing. This all helps the Hadoop programming to be more efficient and revolutionize the task scheduling, which makes it more and more better for the human. Then comes the map reduce workflow in the Hadoop. The workflow starts when a user submits a job. specifying their mapper and reducer logic alongside the job config. So then the task division is done by the job tracker. The job tracker splits your job into many smaller map and reduce tasks according them to the data's layout in HDFS. The map task and education. Task trackers execute map tasks on the local data to maximize efficiency. Then the shuffle and sort. Once all maps are done, intermediate results are shuffled across the network and sorted by key, grouping all relevant data. Reduce and output. All the tasks are run on the final result are stored back in the HDFS ready for consumption and downstream. Let's take the example of a word count application like the hello world of map reduce. Like we takes input of text files splitting into chunk distributed across HDFS node. Then there is the map. It emits word comma one pair for each word encounter. It shuffles and sort, group all counts by unique value, reduces the sum count to get the total occurrence and get the output, word frequency stored in the HDFS. So you can develop a map reduce application involving several steps. We can write your custom mapper and reducer class, often in Java or Python or in other languages that works really good. This is a classic word count application example. We have the input gigabytes of text files spread across HDFS, and we got the map which got emitted for every word count. We got groups of all keys. This basic template is used for analysis ranging from log analysis to market bracket basket analysis, recommendation engine, and more. So this is all for it. Then the next slide. Programming. The programming is a very important concept in Hadoop. How you customly write programs, we can write in Java, Python, and other languages, but your input and output format should be defined using the Hadoop API. Use Hadoop command to submit the jobs and then track them in real time. While the job via the job tracker interface, Hadoop streaming allows any executable that reads from standard input and writes to the plug as mapper or reducer, usually increasing flexibility. This helps to give more advanced programming in Hadoop. What are the advantages and challenges? The main advantage is the scalability. Handles large data growth by simply adding more servers. There is fault tolerance. Resumes from hardware and software failures with zero manual intervention. There is the concept of parallelism. Distributes work for massive gains in speed. Large language flexibility. Beyond Java supports Python, Ruby, and more via Hadoop streaming. The challenge is the batch processing model isn't suitable for interactive or real-time needs. Intermediate outputs write back to the disk that can create the bottleneck for latency. Complex or iterative workflow require chaining, which can increase the management overhead. What is the future of big data processing? While newer frameworks like Apache Spark has emerged and pushing in memory processing and real-time analytics, MapReduce remains the foundation for batch jobs. It's proven at massive scales with deep dive integration with HDFS, HBase, Hive, and more. The MapReduce pattern inspired many model systems, so marketing and mastering it gives you insight for the mechanics behind the next-gen tools. Conclusion or call to action. In summary, I would like to say the map, Reduce, and Hadoop are the must known technologies for anyone who is serious about data structures, big data. They turn impossible analytics tasks into manageable product thanks to their architecture, reliability, and at a scale production. If you want to unlock the power of distributed computing, mastering map reduce is a non negotiable step. Now let's go beyond what's there in the theory. What is exactly used in the real world? First is the web indexing by Yahoo Google. MapReduce was originally built by Google to index the entire web. Imagine billions of web page each mapper crawls the process imaging while reduces merge the word frequencies to link and build the massive search index we use daily. Log processing and fraud detection. Companies like Facebook and WhatsApp and Netflix and Amazon analyze terabytes of server logs daily. The map extract the relevant field, user IDs, timestamp IPs. Reducers aggregate these to detect the anomalies, frauds, or performance issues. There is the bioinformatics and scientific research. Genomics reducing generate petabytes of data. Map reduces pipeline help in alignment, protein analysis, and pattern matching. There is the concept of recommendation systems. MapReduce use e-commerce platform which goes on clustering and saying the co-purchase pattern like which users brought the which and they brought also this, so we create a kind of a networking pattern. We map the pair item from SIM card. We reduce and aggregate frequencies to generate recommendations. There is the sentiment and social media analysis too. Hadoop based MapReduce job processing millions of tweet and posts every day to determine the public opinion in real time matches. What are the takeaways? Whenever the data is too massive for the single computer to handle, the MapReduce divide and conquer it into summarized way. Optimization is bad and best practices we can use here. Even though MapReduce is powerful, writing efficient jobs requires strategy. Let's cover key optimization techniques you should know. First is the combiner function, the mini reducer that runs after map task to reduce data volume before the shuffle phase. Example, in word count, use the combiner to locally sum up all the counts before sending them into the network. Second is the proper partitioning. Ensure related data lands on the same reducer using custom partition. This balances the load and prevent the hot reducers. Compression. Use intermediate data compression to cut down the shuffle and disk IO. Speculative execution. If one node is slower, Hadoop duplicates its task elsewhere to avoid bottleneck. Tune the number of mappers and reducers. Too few, underutilized cluster. Too many, excessive overhead. Rule of thumb, one mapper per data block, which is default of 128 MB, and reducer based on the output size and CPU. Avoid small files. HDFS isn't designed for small files. It is combining small files into a large sequence of files to improve the performance. Also, there is a difference between MapReduce and Spark. A quick comparison can be done. Like a common interviewer or Viva question can be, why we use MapReduce when Spark exists? So the answer for this would be, MapReduce processing is based on disk-based batch jobs, whereas the Apache Spark uses in-memory computation. The speed is slow due to the I/O. Apache Spark has a fastest speed. Fault tolerance, it re-executes the field task, whereas the Apache Spark resiliently distributes the dataset. So the map reduce can be used for long and batch processing heavy tasks, whereas the Spark is used for real-time streaming and interactive ML, which requires a little less load. So the Spark often complements or replaces the MapReduce in modern terms, but MapReduce still remain essential for the foundation understanding, legacy system, or the ATL batch pipeline still used across industries. By looking at the interview angle, I can say that MapReduce has some common questions which should be analyzed, like how does Hadoop achieve fault tolerance, how it shuffles and sort with examples, what is the difference. So these all gives us a final idea. Whether you go on the master, spank, flick, or any future framework, remember they all stand on the shoulder of MapReduce. So keeping experimental, deploy small Hadoop structures, write your own mappers and reducer, and visualize the magic of these distributed happening behind the scene. Thank you all for staying till the end. If you found the deep dive valuable, hit that like button, subscribe. Thank you so much for watching.